Traditional software engineering relies on rigid, formal languages. When you write a script in Python or execute a query in SQL, you map specific syntax directly to a deterministic output. Assuming the environment is stable, giving the system the exact same input twice guarantees the exact same output every time. Analytically, this diagram contrasts that rigid structure with the reality of large language models. You submit an input using informal natural language, and the system executes probabilistically. You are no longer mapping syntax to an outcome, you are mapping a prompt to a probability distribution. If you feed a conversational, vaguely defined instruction into a production LLM, the model must resolve that ambiguity on its own at inference time. The result is unpredictable, unstructured prose. To understand why, we have to look at the baseline mechanics of autoregressive generation. An LLM operates by predicting the next logical token based entirely on the preceding context. Relying strictly on next token prediction without applying severe structural constraints causes logic to degrade rapidly. In high-stakes applications within fintech or medical diagnostics, this variance creates unacceptable risk. There is also a strict financial penalty for variance. Under standard API economics, processing an output token costs 3 to 5 times more than processing an input token. An unconstrained model that wanders through paragraphs of irrelevant reasoning burns capital. Without a rigorous engineering layer placed between the user and the model, an LLM operates as a volatile black box. It cannot function as a reliable, parsable software component on its own. This visualization represents how a model samples its next step. Based on the current context window, it generates a vast probability distribution of potential next tokens. When you provide ambiguous instructions, you flatten this probability curve. The model is forced to guess your intent, assigning similar likelihoods to widely different responses. You can adjust the API temperature to govern how randomly the model samples from this distribution, but temperature cannot inject missing logic. It alters the randomness, but it does not provide structural clarity. The objective of advanced prompt engineering is to manipulate the context window's vector space to artificially collapse that probability distribution around a single specific outcome. At this level, you stop treating prompts as natural conversation. Every character you send to the API acts as a rigid engineering constraint. You are applying enough contextual pressure to force a probabilistic engine to simulate reliable, deterministic behavior that a backend API can parse. Writing a production prompt requires compiling natural language into a highly controlled software pipeline. Modern LLMs manage thousands of tokens of conflicting context by enforcing a strict priority ordering known as the instruction hierarchy. This pyramid illustrates that hierarchy. The system prompt sits at the peak. Controlled exclusively by the application developer, it acts as the highest authority lever in the pipeline. Below it are the user input, the assistant's own historical output, and the data fetched from tool and function calls. The hierarchy ensures that instructions from these lower tiers are prevented from overriding the system prompt. This establishes your primary security perimeter. In application design, user input must be treated as inherently untrusted and adversarial. Prompt injection attacks operate by targeting this stack. Malicious inputs attempt to trick the model into elevating a user command above the system rules established by the developer. The lowest trust tier in the hierarchy belongs to injected tool data. When an LLM executes a web search or database query, the fetched content may contain malicious payloads that the model will ingest as context. A rigidly defined system prompt serves as the only structural defense capable of blocking these external variables from hijacking your core business logic. To build that defense, a production-grade system prompt requires 6 anatomical components. The first component is the role or persona. Assigning the model a specific identity, like expert data scientist for Acme Capital, immediately shifts the initial probability distribution towards specialized, domain-specific terminology. Next is the task instruction. This is a precise, unambiguous directive defining exactly what action the model must execute, such as analyzing a specific time series array. If this directive is vague, the model will attempt to resolve the ambiguity on its own at inference time, leading directly to hallucinations. The third component is context. Injecting retrieved background documents and hard business rules grounds the model's response in factual data, rather than relying on its pre-trained weights. Processing massive context blocks can be computationally expensive, but utilizing prompt caching on repeated prefixes cuts inference latency and token costs by up to 90%. By combining role, task, and context, you build the rigid operational boundaries the LLM must obey before it generates a single output token. The fourth component introduces in-context learning through the use of examples. Providing exact input-to-output mapping pairs demonstrates the desired behavior. This drastically improves output reliability without requiring any gradient updates to the model itself. The fifth component consists of constraints and rules. You yield better compliance by using explicit, affirmative statements. Telling a model to return only JSON outperforms a negative instruction like do not return prose. Notice the formatting. Using all caps draws disproportionate attention from the model's attention heads, forcing it to weigh that specific constraint heavily. However, you must limit your scope. Exceeding 10 to 15 explicit rules degrades the model's ability to comply with all of them simultaneously. You also have to account for the lost in the middle effect. As context length grows, models tend to ignore instructions buried in the center of the prompt. Critical constraints must anchor the very beginning and the absolute end of the context window. The final component is the output format spec. This enforces the exact structure of the data the model returns. Explicitly prohibiting markdown wrappers and defining your exact data types eliminates the need to write hundreds of lines of post-processing code to extract the values you need. Layering these 6 specific components strips away the conversational interface, systematically collapsing the model's output variance until the result is a structured, predictable JSON response that a backend can finally trust. Standard zero-shot inference works for simple extractions, but it fails consistently on complex mathematical tasks or multi-step logic. Forcing an autoregressive model to output a final, calculated answer in a single forward pass forces it to skip the necessary intermediate logical states required to reach that answer. To solve this, we use chain-of-thought prompting. This sequential diagram illustrates how the technique forces the model into a linear, step-by-step execution path. By generating intermediate tokens, the model actively alters its own context window in real time. It feeds its own logical steps back into its subsequent predictions, drastically improving final accuracy. It creates a forced sequential dependency, where step 3 cannot resolve until the calculations from step 2 are locked into the context. This emergent reasoning ability is a function of architectural scale. Models below the 100 billion parameter threshold often lack the associative density to sustain a multi-hop chain, frequently causing the logic to collapse into circular patterns before reaching a conclusion. By requiring intermediate steps, you are artificially expanding a logical proof across the time dimension, forcing the model to map out its rationale before it generates a final answer. Linear chain of thought has a distinct vulnerability. If the model hallucinates a single step early in the process, the entire downstream sequence is corrupted. This branching diagram illustrates the tree of thoughts framework. Instead of a single chain, it allows the model to explore multiple parallel reasoning candidates simultaneously. The framework prompts the model to self-evaluate its own intermediate states. If a path proves illogical, the model prunes the dead end and reallocates compute to stronger branches. The system utilizes breadth-first or depth-first search algorithms, actively navigating the generated reasoning tree to locate the optimal target outcome. It is an active navigation of a vast probability space, testing thousands of potential dead ends to map out a single viable path. Multi-path generation incurs a massive token cost, but for complex algorithmic reasoning, it delivers an extreme increase in final output reliability. Advanced prompt engineering transcends writing natural language into a chat box. It is the precise discipline of manipulating token probability spaces to architect rigorous, production-grade AI systems.